So what's up, ladies and gentlemen, and welcome to the solution review on this channel. And today we're going to solve problem 23. 23. It's a problem about it's about two coils, where one of the coils has a current, and this current produces a magnetic field in the other coil, in the little coil. And the letter A asks you to determine what's the total magnetic flux across the little coil. So he asks you, and to solve that, the question actually helps us, because the problem says that the magnetic flux or the magnetic field in the region of that little coil is actually approximately constant. So we don't have to take any integral or something like that. So we only have to multiply the B field by the area of the little coil. So the one thing that we have to determine right now is the B field. You may remember the right expression for the B field in this case, but I think it's useful to discover this expression right now. So and to do that, you may use the Biot-Savart law. I think you should remember the Biot-Savart law, especially if you pay physics 3 or electromagnetism. So this is the expression for the Biot-Savart law. What you can do now, you can see that this ds element of a line vector product, this radial vector, equals ds times the sine of alpha. Alpha would be this angle right over here. And you have to remember that the magnitude of the vector hat equals 1. Since this is a unity vector, but so the next step is to substitute this expression in the B field. And you may also see that the sine of this angle equals the R uppercase divided by the R lowercase. So the B field equals the permeability, magnetic permeability. I hope I'm not confused with magnetic susceptibility, divided by 4 pi. This is the current, and this is ds R lowercase squared, and the sine. So we are integrating in ds. ds is the element of a line. It goes from 0 to the total length of the circle, 2 pi R uppercase. So it's actually very easy to do this now, because all the expressions get out of the integral sign. You have R lowercase to the third, and you have this expression here. When you integrate the ds, you get 2 pi this uppercase. Let me stop. We have determined the magnetic field. We use the Pythagoras. I think it's Pythagoras, the right name. I don't remember these names from high school. Well, we use Pythagoras, I think, in this expression for the R lowercase. So we don't have to multiply this magnetic field by this R. But before doing that, the problem actually help us, because they say that the axis is much greater than the R uppercase, and so you may make this uppercase, tending to 0. So you get a B like this. Half to x to the 3. This is 3. This is, oh, I'm making horrible. Uppercase squared. So this is the magnetic field, and you only have to multiply to obtain the magnetic flux. You multiply by the area of the little coil, and I think you know the area of the little coil because that's a thing from high school. So P lowercase squared. So this is the expression for the magnetic flux across the little coil. So we go now to the letter B. I think we can solve this letter B here. I hope there is space. So letter B asks you to determine the electromotive force. You may remember that the electromotive force has a relation with the variation of the magnetic field. Because when you vary a magnetic flux, you produce an electromotive force, or let's call in a more common way a voltage in the circuit. So you have, this is the right expression to use. And to derivative this thing with respect to the time, the only thing that depends on the time actually is the axis, because as the problem says, the little coil is going away from the bigger coil. It's like running out of the bigger coil. So we get minus, this is minus, magnetic permeability, current, this is 2, a lowercase square, uppercase square, pi, I hope I'm not forgetting any letters, and the derivative this 1 over x, I hope you can understand that, 1 over x 3 with respect to the time. I'll put this way. So to derivative this thing with respect to the time, you use the chain rule, because I'll repeat this expression here to be more clear. You get minus 3 x minus 4, the derivative of x with respect to the time. So the final expression for electromotive force will be 3, because you have a minus sign, pi magnetic permeability, square, uppercase square, 2x to the 4, the current, and the velocity, because the velocity is actually the derivative of x with respect to the time. So I understand that this is, I'm sorry this is not so clear, my letter is not so good right now, and the space is not so convenient, but this is the right expression for the electromotive force. So we now go to letter C. I think letter C is more easy, and I can explain that with this drawing, with my drawing that I did in the letter A. So the letter C asks you, what's the direction of the current? Well, you know that the little coil is going away from the bigger coil. So if the little coil is going away from the bigger coil, you expect the magnetic flux to decrease, because the magnetic lines will be more, how can I say that? Will be going, will be more, less dense. I think this is the name. So and the magnetic flux is decreasing. So the current produced in the little coil, which is getting away from the bigger coil, is the one who will produce a magnetic flux that will try to maintain the total magnetic flux constant. So if you have a little coil here, the current will be in this direction, because a current in this direction, for the ones who can see well, this is the counterclockwise direction. Counterclockwise direction. And the current right here is in the same direction. So because if you have a current in this direction, the magnetic field produced by this coil will produce a flux that will sum with the flux of the bigger coil. So it's like the flux will maintain, will not maintain constant, but will try to maintain as constant as possible. So this is a way to think about. So I hope you have enjoyed the video. I hope as well you guys have a beautiful day. Bye bye.